Okay. So, my name is Clement Escoffierr. I'm working for Red Hat, and I'm going to present to you briefly how to build reactive distributed system with Vertx. The first thing we need to discuss is what Vertx is. Vertx can be summarized by this sentence. Vertx is a toolkit to build distributed and reactive systems on the top of the JVM using an asynchronous non-blocking development model. That's a lot of buzzwords that we will define. So the first one is a toolkit. Vertx is not a container, Vertx is not an app server, Vertx is not a framework. It's a toolkit. So it's just a plain boring jar that you can put on your class path. Once it's done in your class path, then you can start using Vertx. All the Vertx components we deliver are just plain boring jars. There is nothing smart or nothing complicated. But thanks to this, you can use it everywhere. You can use a class path, you can use them in a fat jar, you can embed them in a war, you can embed them in a ERR, you can embed them everywhere because, well, there is nothing smart behind this. This slide here are actually Vertx applications. All those slides are served by Vertx. And we are going to see that it's actually not a simple Vertx application. It's a clustered application, and we'll see all the other components I'm going to start are interacting with these slides. So these slides are here. It's just a jar. Then we have two dependencies, Vertx Web, that is a component to build a modern web page and modern web app with Vertx, and a cluster manager which will be Hazelcast in this demo, and a couple of dependencies. In this demo, everything is packaged in a fat jar, but we don't. That's just a detail. Vertx is made to build distributed systems. There is no better definition of distributed systems than this one, which means a distributed system is going to fail. Anyway, it's going to fail. You can do whatever you want, it's going to fail. So you have to live with that, you have to deal with these failures. And one other thing is, it's not any kind of distributed system, it's a reactive system. A reactive system has been defined by this manifesto here a couple of years ago, and are built on 4 characteristics. First, it's responsive. Responsive means that your system is going to respond to the request in an acceptable time. Acceptable depends, of course, of your use case. It's elastic. Your load is going to evolve, so you need to be able to scale up, scale down, change things, kill nodes, restart new nodes, and so on. It's resilient. Well, as we said, distributed system fails, so you need to be prepared to handle these failures. And it will be built on an asynchronous message pacing, because asynchronous message pacing will let you implement location transparency, loose coupling, and so on. So, something to understand is the difference between reactive programming and reactive systems. There is a lot of talk at Java 1 about reactive. If you go to the agenda and search for reactive, you will have probably 25 talks. But actually, there is two meaning behind reactive. Reactive means showing a response to a stimulus. That's not from me, that's from Oxford. And from this, there is 2 branches. The first branch is reactive programming, where the programming mode level. It inherits from functional programming, and it's actually just a subset of functional programming where you handle streams. A stream is a sequence of data, error, and end of streams. So you just have a pipe where you have data inside, and you observe this pipe. Every time that there is a data or one of these events, you will be notified, and you produce another stream. You have to produce another stream to stay in the reactive programming paradigm. So here we have all the RX library, RX Java, RX JS, RX Groovy, and we have also Spring Reactor, which are reactive programming. While Vertx is a reactive system, we are not at the same level, we are at the architecture level. It will still show a response to a stimulus, but the stimulus are not a stream, the stimulus are messages, the stimulus are failures, load, metrics, and so on. What you build as a reactive systems is actually a living body, where every time you do something, it's going to react. It inherits most of its concept from dynamic and autonomic systems and actors and agent systems. Something to understand is that functional programming was defined in the 60s. Actors and agent system was also defined in the 60s. So there is nothing new here. Actually, in this whole presentation, there is nothing new, just recycling stuff. So here, as a container, we have AK and we have Vertx. So, the last part of the definition is it runs on top of the JVM. That doesn't mean it has to be developed in Java. We are Java 1, so all the code that I will show here will be developed in Java, but I could have used Groovy, Ruby, JavaScript, Ceylon, Scala, or Kotlin. So Vertx, the toolkit. So we will build distributed system. There is two ways to build distributed system. You can use a framework that will hide the whole complexity, or you can use a framework that will let you handle this complexity, because anyway it's going to fail. So it depends on your passion in debugging live system in production, but generally we don't really like doing debugging system in production. So you need to have a way to handle this complexity, and that lets you handle this. Failure will be a first-class citizen, and Vertx is not an all-in-one solution. It's just providing the building block. So which building block? So we will provide you TCP, UDP, HTTP 1 and 2 server and clients, WebSocket, of course, non-blocking DNS client. This is actually very important. Every time in Java where you resolve a DNS, new URL with a name, actually this is a DNS request which is blocking. If your DNS server is slow, your code is going to be slow, and you have nothing to do. It's inside the JVM. So in Vertx you have a non-blocking DNS client that will handle that. Clustering, so built-in clustering, built-in event bus, distributed data structure, built-in load balancing, built-in failover, pluggable service discovery, circuit breakers, metric shell, and a lot of other things. So this is just a small part of the components we provide. We will build reactive systems, so the applications that are built with Vertx are going to be fast. I will show you some numbers at the end of this presentation. You will see it's really, really fast. It's going to be elastic. It will scale up and down. And you will do that by just starting a new node. Nothing complicated. And it will dispatch a load among all the nodes that you have started. It's going to be resilient. Failure will be a first-class citizen. You will see the code might look a bit complicated at the beginning, but actually it's new platforms are built with failure as a first-class citizen. If you look at JavaScript or if you look at Go, failures are there. So in Go, you have to check that it was not a failure after every call. We have a built-in failover, and the asynchronous message passing will be based on a asynchronous and non-blocking development model. How does that work? In traditional Java development, when you want to deal with a database, for example, you are stuck. You will do your select or your query, and you wait for a reply. You wait until the database are managed and computed the result and give you the result. Well, in a non-blocking approach, it won't work like that. We will enqueue the request, pass a callback, then the thread is released. As it's released, it can do something else like B, C, then get some free time, handle some more stuff, and when we have the response from the database, we will continue the task A. This may or may not happen. Remember, distributed system. That doesn't mean that it's going to work. It means that it may fail at any time. How it looks in terms of code? Well, generally you was doing this. Do something A, B. And actually, with an asynchronous development model, you will do the same thing, do something, you pass the parameters, and the last parameter is going to be a callback. Okay, what about callback? Callback can become very complicated very quickly. So we have a second way to write exactly the same thing with futures. That's not Java futures, that's Vertx futures. Java futures are blocking. Vertx futures are non-blocking. So here, your operation, you just pass your parameter, is returning a futures, and when these futures will be completed or failed, then this handler here will be called. With futures, you can compose them quickly and efficiently with do that when this is done, or wait for all these futures to be terminated successfully, and so on. So let's start to see some code, and we will start with very simple paradigm, which is a request reply, and as HTTP and REST as ruling more than, well, mostly all the application right now. We are just using HTTP for this demo. The first application you will do in Vertx is this. You start a Vertx, you get a Vertx instance here, and you start an HTTP server. As I said, Vertx provides a HTTP server by default, so you just do create HTTP server. When we build an HTTP server, there is two things that are important. The first one is, what do we do when we get a request? So we attach a handler here, and we say, well, when I get a request, I will just say world. The second thing, and every time I get a request, I will execute this. The second thing is this listen here. Starting an HTTP server is going to take time. There is many things that need to happen at the operating system level to discuss, to negotiate the sockets, to be sure that the port is available, and so on. So this operation is asynchronous and may fail. So the AR that we have here is actually an async result. That means the structure that will contain the result of an asynchronous operation. So here we can say, okay, did it succeed? Yes, okay, so that's fine. Or here is a stack trace. So here, it's an async result, and as it's an async result, we have to handle the failure here. So already here in this very simple snippet, we have the failure of the first-class citizen. Okay, but let's have this running. So this is this code here. It's mostly the same code. I just extend it a bit. Like I use a simple date format. Well, as a Java developer, you should say, well, come on, this is not thread safe. This is going to be a failure in production. We are going to see that. Then I just want to also print here the name of the thread, and we will see that. So I'm going to start this. Remember, Vertx is not a container, an app server, it's just a toolkit. So to start a Vertx app, it's very complicated. Run. No plugin, nothing. You take your IDE, you just start it. You don't need any plugins, you don't need anything. It's just a main. So it started on the port 8081, and if I go back here and do invoke, you see, that's my date, and well, that's a weird thread name. Look, and it's always the same. It's always this event loop thread 2, but what is this? What does event loop means here? An event loop is very simple. It actually can be implemented with 4 or 5 lines of code. It has somewhere a queue of events. Events are just passed by event provider. We don't need to know what they are. It's just a queue of events. And this event loop will get the next event, find the interested handlers, and dispatch the event. That's very simple. As it's a thread, and it's a single thread, well, that's very simple because actually you don't need to do any concurrency or synchronization construct because there is a single thread. So you can have deadlock, you don't need synchronize, you don't need volatile because, well, there is a single thread. That's exactly the same concept that you have in Node, the same concept that you have in Android, and so on. This development model, this model is actually very powerful but has one main drawback that involves the golden rules of Vertx. If one of your handlers here is blocking, is expensive, takes some time, so stuff like that, what is going to happen? Well, the thread is stuck. So as the thread is stuck, the event provider will continue enqueuing events and events and events and events, and nothing will happen because here you are stuck. At the end, you will run in and out of memory. So the golden rule is very simple. Never ever block the event loop, or the whole model collapses. If you don't block the event loop, this is going to be pretty fast. I will show you the performance at the end. It's really, really fast. Okay, so we saw how we serve, how we can have a server, but we can also have an HTTP client. Vertx comes with a built-in asynchronous HTTP client, and we create one like that. Vertx.create HTTP client. We set the host, we set the port, and then we say, well, okay, I will do a GET request on slash. Here is what is going to happen when I will get a response. And actually, HTTP is interesting because when you get the response, you just get the status line and the headers. You don't actually get the body. The body can arrive later. So that's why, if I'm interested in the body, I need to register a body handler that will get the body. Buffer here is just a representation of byte array, just a byte array actually. So if I do that, that is going to be this code here. Exactly this, what we have shown. So here I just do the, that's up now, this one here, yep. So that's exactly what I've shown in the previous slide. So I will just do my get now, and then I get the response. I am interested by the body, and so I read the body. And as here, I'm doing the second way without callbacks. I just return a futures. When I have the body, I just complete the future, so I give a value to these futures. It can come at any time, I don't care, because as soon as I do future.complete, then this handler here is going to be called. So now if I do that, we will have my browser, so this application here, that is calling a server that is using the HTTP client, and that is calling the server that I've started in the previous demo. And if I do that, did I start it? Oh, I forget to start it. So if I don't start the application, then it doesn't work. that also works for non-distributed application, actually. If you don't start the application, it doesn't work. Here we go. As soon as I start the application, things are much better. So we have the hello that is prepended by B. The Java one was coming from A, and now we have this. Obviously, we are still using the same thread. So right now in this system, we have my slides, which are a Vertx application, B, which is a Vertx application, A, that is a Vertx application. We're already a distributed system with 3 nodes. Let's go a bit further, because, well, that's just request reply, but let's go and do some messaging. Vertx comes with a built-in messaging system, which is named the event bus. It's a nervous system of Vertx. Every Vertx application is going to use at some point the event bus. It's very simple. It has 2 concepts, address and handler. Good news, we already saw handlers. So handler are just a callback that will receive the message. Address is how we address message. We don't have hierarchy, topic, queue, or stuff like that. It's just opaque string. If you want to use space or tabs, you can. If you want to use UTF-8 or weird character in your address, you can. If you use only space and tabs, well, you can, but that's going to be hard to debug, but you can. Once we have this, the event bus will provide you 3 ways to deliver the event. The first one is point-to-point. You send the message to an address, and you have something else that is listening to this address and get the message. So how it works, from the Vertx object, you can get the event bus. You send on this address and a message. Here, just a string, but it can be an object. And on the consumer side, you just register a consumer on the same address. And here is my handler. When I get the message, I do that. So here I do nothing. A message is very simple. It has a body and a couple of headers. Obviously, we have publish, subscribe, same thing. So instead of send, I'm using publish. And we have a third delivery pattern, which is kind of interesting in request response. I have a sender that sends a message to an address. A consumer receives it and has the possibility to reply to this message. So on the send side, I send to address. That's my message. And I say, well, when I have a reply, just do this. So I append a handler to my call, and this will be as a reply handler. And on the consumer side, when I get the message, I can reply. So let's now imagine that the message that go out say, okay, method foo, param1, hello, param2, java1. Well, and the consumer is just returning, replying with hello, java1. This is RPC. We can implement a full RPC system based on this asynchronous messaging system. So it's an asynchronous RPC, sorry. Obviously, an event bus, if it just local to a node, that's not actually very interesting. What would be cool is to have this event bus distributed among all the nodes that I have started. So to do that, instead of doing the vertex.vertex, I just do vertex.cluster.vertex. I pass some options, here I don't care. Then I pass a result, because it's an asynchronous operation. Joining a cluster is kind of long, because there is lots of negotiation. First, we need to be sure that the cluster exists. We need to join it. We need to wait until the consensus is computed. So it's really an asynchronous operation that can take time and can fail. But once it has succeeded, then you get your Vertex instance like that. And all the examples that I've shown works. So what is cool that every time I start a Vertex node on the cluster, the event bus is going to be distributed. But the event bus is so simple that it's not limited to Vertex. We can have a TCP, we have a TCP bridge, so all C, C++, .NET application can interact using the event bus. We have Node.js, and I'm going to show that in a second. Node.js can also be a member of the event bus and send and receive message. And my browser here, this browser here, is going to receive and send message on the event bus. So, oh, there is something running in the background, cool. Here I'm going to start this application here, which is going to send a to publish a message every 2 seconds on the event bus on this address here. Oops. Here, okay. So I'm starting that. So here we see it's starting to join the cluster, and I have a cluster of 2 nodes, my slides and this new application. And once it started, we see that we have hello from and now a counter, so 2, 3, 4, 5. Okay, but now we have a Java application that is sending message to my slides. How does that work? To my slides. That's my browser, seriously. And I'm really not a web developer, so believe me, I'm unable to do anything in web development. But let's go a bit further. If I go to my terminal here, and I do npm start, look, hello from bonjour from Node. Now we have a Node application that is sending message to my slides, passing by the event bus. So I can show you the Node application. It's very simple. You just get this npm here that we provide. No, that's here. So from this npm, you just create the event bus. Oh, that's an interesting address. From where does it come? We are going to see that. That's actually the bridge address. And then, once you have opened the event bus, you can just send message or publish message. Actually, it will work with publish too on the event bus. So how does that work? Like that. That's my. That's actually the Vertx application that hosts my slides, and it has a SockJS bridge. SockJS is a JavaScript library that will negotiate a protocol between Node and the browser. So it will start by WebSocket and degrade to iframe with a set of steps, or SSC and so on. And this bridge is going to be used by Node and by my browser to be connected to the event bus. So my Node publisher connects to this bridge, send an event. The bridge sends this event to the event bus, which come back to the SockJS bridge because my browser here has registered also on this bridge to say, well, I'm interested by this address. And when you get an event on this address, send it to me. So it's used a WebSocket in both cases here because Node.js is really good at WebSockets, and I'm using Chrome, so it has WebSockets too. And my Java publisher here, actually, is just sending message on the event bus, as we've seen in the API. So I'm going to stop a couple of things now. Okay. So that's good to do distributed application, but again, they're going to fail. And they're going to fail a lot, believe me. So be prepared. You will have to handle your failure by yourself. We are not bulletproof, we are humans. We are all making bugs, and the hardware and the physics behind networks and so on is going to make failures too. So you need to handle these failures. We already saw that, actually, with my asynchronous result. Asynchronous result is a structure that contains the result of an asynchronous operation. An asynchronous operation can fail, that's what we check here, or can succeed. If it fails, you can have the reason, that's the cause, it's an exception, or here, if it's valid, then you can get the result. Another way to handle failure is to set timeout. It's actually a pretty bad way. In 1985, oh yeah, I'm a former academic, so I'm going to cite a couple of very old papers and stuff like that. But in 1985, some researchers have proved that we can't use timeout to be sure that an operation has failed. And it makes a lot of sense. I have A and B. And I say, okay, if I don't have if I'm calling B, and if I don't have the reply in 1 second, that means that it's a failure. That's not true. That means that the message to go to B may have failed, or the operation that happened to B may have failed, or the message on its way back may be lost. So that the operation may have succeeded, but for us the timeout will be still strong. So all our operation in Vertx can have a send timeout or a timeout, so sometimes it's configured differently. And when you have a timeout, what happens is that it will use this asynchronous result and consider it as a failure. Again, that doesn't mean that the operation didn't succeed. It means that we didn't get the result in this 1 second. Our timeout is in milliseconds matter. Another way, very popular in the microservice world, is to use circuit breaker. So again, circuit breaker has really old. It's something that was invented in the 70s in operating systems. Circuit breaker is just a 3-state automata. It's really very simple. You start in the closed state, and here every time that one of your interaction is failing, you just keep track of the number of failure. And once your number of failure reach a threshold, you go to the open state. In the open state, you won't execute the operation anymore. You will go to a fallback immediately. Periodically, and that's what it's called with a circuit breaker, periodically it will try to go to an half open state. In the half open state, it will take the next request and one request only, and will try to execute the operation. If the operation succeeded, then, well, everything's fine. I go back to the closed state. If it failed, then you go back to the open state and wait for the next attempt to go to other half open state. Why it's very important? Because when you fail, when there is a failure, you can cascade the failure, bubble up, and your whole system can die. Or you can contain this failure to a single node. Well, you can do that with a synchronous result, but what does circuit breaker give? It gives time for the system that is failing to recover. And you won't stress it, because as soon as you are in the open state, you will execute a fallback. So you won't stress a system that is in really bad shape and need to recover, need to take a breath, to be back, to take some fresh air, and once it's back, thanks to the half open state, you will recover. Vertx has its own circuit breaker. Of course, you can use these tricks. Of course, you can use any other circuit breaker, but we provide our own one, which is integrated with in a non-blocking system. Another thing that is actually important is, okay, circuit breaker is for failure, but what happens when the whole node crash, seg fault, out of memory? Well, all those things that, well, may happen. It's going to happen. We have leaks, we have seg fault because we are using GNI, so at some point, something is going to crash. Vertx provides a built-in system to handle this. Actually, for introducing this, I need to introduce one other concept, which is vertical. A vertical is just a chunk of code, just a class, that get deployed and run by Vertx. A vertical, so here can deploy other vertical and so on and so on and so on. So it's kind of a component model. It's a very lightweight component model. Vertical can be written in any supported language, so Java, Groovy, JavaScript, Ruby, Ceylon, Kotlin, Scala, and so on. When we start Vertx in high availability mode, and one of your machine of your cluster is crashing, Vertx detects this, and will take all the verticals that has been deployed, and will deploy them automatically on another node of the same cluster. You don't have to buy an expensive solution, it's all provided. So generally your cloud provider can do that. Here you don't need even to rely on your cloud provider. Vertx will do it for you. So here if this machine dies, this vertical here is going to be redeployed automatically on this same node. Well, there is settings that you can configure to be sure on which node it will arrive. I won't show you a demo, but if you're interested by this, I have a full talk on Vertx Wednesday morning, where I will demonstrate all the circuit breakers, this really with live demo. Elasticity pattern. What's the worst thing that can happen to you is that you develop a great app and you start getting success. And then, well, you fail. Because your system starts to be slow and so on. So be prepared to be famous. We never know. You may become rich. There is two elasticity patterns. The first one is vertical scalability and the second one is horizontal scalability. Vertical scalability means that instead of one event loops, remember I have introduced event loops. We don't have one event loops in Vertx. We have as many event loops as CPU cores you have. But it's not because you have that all the synchronization pattern that I've said at the beginning will be broken. We guarantee that. So your code is still going to be single-threaded. You don't need synchronization. You don't need a synchronization construct. But the load is going to be dispatched on all your CPU cores. So a Vertx application is actually going to use all your cores of your CPU. The second thing is, thanks to the clustering, we also have horizontal elasticity. So vertical scalability, because this is fixed, well, you can't add a core to your CPU, or it's kind of really advanced engineering. But horizontal elasticity, because you can increase the number of nodes that you have on your cluster or decrease it. So if you have a lot of users, you start new nodes, and once the peak is over, then you can reduce it. How it works, actually, it will be very simple. Every time you will send a message at the event bus, instead of always sending to the same customer, it will just implement a round robin. So if you have a lot of messages, the sender will be, the message will be handled first by A, B, C, back to A, B, C, and so on. And when you get less load, then you can kill C. Then it will be just A, B. And if you really have almost no traffic anymore, well, just kill B. Then you, let's say your Amazon bill that you will pay at the end of the month will be much smaller if you have only one node, and then you scale when you have a peak of load and so on. So Vertx will handle that for you. Round robin is built in. Okay, so that's not the end. What I've presented is almost only Vertex core, so it's this part here, but there is many other things. We have asynchronous RPC, we have a lot of things around TCP, we have Vertex Web that is used to build this application, we have clustering, we can use RX and reactive programming to build your reactive system. 2 times reactive, not the same meaning, so reactive programming to build your reactive system. We have Docker support, we have MQP bridge, we have Mongo, we have GDBC, because yes, you can deal with GDBC. GDBC is a blocking system. We provide you an asynchronous client. We have Stomp, we have service discovery, we have integration, we have Camel somewhere, yes, here. So you can integrate reactive system with all your legacy applications that exist right now, thanks to Camel, and so on and so on. We have GCA if you have Java EE application, we have HTTP2 and so on. If you're interested to go further, first the Vertx website, vertx.io. Then there is this blog post series here that is really for developer, but will accompany you and build your first Vertex applications with testing, integration testing, and so on. And that will be an application to manage my collection of bottle of whiskeys. Yes, I developed it, and it's actually used by me. And then there is a hands-on lab that will be Thursday noon, and there is the talk, which is Wednesday morning, so check on your agenda. If you like Vertex, vote for us for the JAX Awards. That would be great if we can win this innovation award. I said about performance, so let's have a quick look. We don't run this, that's Tech and Power. That's preliminary data, but it's almost final. We are here. We are in the top 5. 1, 2, 3, 4. We are 6. So we are in the top 10. Most of them are just pure native. We are based on Java. We are faster than Netty on this benchmark. All benchmarks will show similar results. That's all for me. If you have questions, I will be around the booth. Well, thank you very much.